to actually form an image out of them. This technique allows real-time imaging because it takes typically half a second to get an image, and nice lateral resolution of 10 to 20 nanometers in the normal direction. We're able to resolve the atomic planes. It has one drawback, is that you need to have atomically clean and very high quality surfaces because it's so surface sensitive due to this low energy that you really need to have clean surfaces. But we try to turn this weakness into a strength, and because of that, we have to think of our system as an NB system instead of a beam microscope. So we have a sample holder here, which can go from 100K to 1500 degrees C's. We have 8 evaporator positions where we can feed metal vapor, we can feed oxides, reactive gases. So a lot like an NB system, but instead of having a read gun to monitor what's going on, we have actually a beam microscope attached to it, which gives different and perhaps a little bit richer information. So what I just said is means that this is a very suitable technique for in situ experiments. We like how to grow the sample inside. And actually, the example we did today is one of the few examples where ex situ grown samples were actually we were successful with that. It's a nice data out of that. So what I just said is common to all beam microscope, but in this case, what you have is a spin-polarized spin microscope. And the difference is that at the electron source with circular laser light, we're able to accept spin up and spin down electrons, and then through some careful combinations of electric and magnetic fields, we're able to make the electrons inside the surface at different spin polarization directions. We can make them go normal to the surface or parallel to the surface, and then also change the angle. And because of that, and because one is sensitive to the magnetization direction but is parallel to the spin polarization direction, we can actually do 3D magnetometry by changing this direction. And then it's quite easy to obtain a magnetic contrast image. We basically take one beam image with a spin out, the other one with a spin down, subtract, and then we obtain a magnetic contrast image. So with this light here, one can get a better idea of what I mean by 3D magnetometry. Here we have an in-plane magnetized sample, this system here, with a vortex state here. And when we probe the sample with electrons polarized normal to the surface, then we see no magnetic domain because the magnetization is in plane. And then by taking 2 orthogonal images from in-plane direction, one is able to map out the 3D domain structure of the system. So what can spin bring to the world of oxides? Well, for one, it can clarify the growth mechanisms of complex oxides, because you can watch them grow as from the very first atomic layer as you're growing. And because of that, you can also check the point at which you get the emergence of, for example, ferroelectricity and multiporosity or ferromagnetism as a function of thickness in the desired system. Because one is able to visualize the ferroic domains. We've talked about how you can visualize the magnetic domains, but also when you're at very, very low energies, like close to what is called the mirror transition, where your electrons are not barely touching or interacting with the sample surface, you're actually able to also see the ferroelectric domains of the sample. So you can study the coupling between ferroelectric and ferromagnetic domains in the system. Also, you could see things like the influence of strain effects due to the substrate in the system. So I know there are many experts in the audience, but bear with me for a couple of minutes because I want to talk about why magnetic domains form, and because as you have seen, magnetic domains is the main topic at which spin thrives. So in any magnetic system, the free energy wants to be minimized, and this free energy has a number of different contributions. I'm only going to focus on this three for the sake of simplicity, but a couple more. And basically, the first one here, the exchange interaction, consists on when you have a system of spins, the exchange interaction is going to align them parallel to one another. But if one only had this interaction, then they would be aligned randomly in any direction in space. Is this second term here, the subject term, but it's going to favor specific crystal orientations of the alignment, usually due to the spin-orbit coupling to the crystal lattice, as you know. But then maybe one could say that the term more responsible for the appearance of magnetic domains is this third term, the dipolar term, because in this picture here, one would get just a single domain magnetic system. But this third term here, the dipolar term, wants to avoid the formation or the accumulation of magnetic poles, and that's why it's going to promote the formation of domains. So why magnetite? I'm sure you all know it has many interesting properties. It was the first magnetic material known to mankind, but somehow it has managed to keep us interested for all these years. There's always something new going on. It is ferromagnetic with a high QC around 800 Kelvin. It is predicted to be a half metal. It is quite stable and robust because it's an oxide at room temperature, which makes it interesting. As you know, it is multiferroic at low temperature. It's both ferroelectric and ferromagnetic. And it is discussed that it could be used in devices such as spin filters or spin injectors, basically because of this half metallicity. And these interesting properties come, as always, due to its structure. Magnetite has an inverse spinel structure with the tetrahedral sites occupied with iron 3+ cations, and the tetrahedral sites populated with a mixture of iron 3+ and iron 2+. So, for example, the moderate conduction that it shows at room temperature is believed to be due to the hopping of electrons between the octahedral sites. And additionally, magnetite presents a very interesting transition called the Verwey transition from conductor or non-conductor to insulator when cooling down below 120 K. And it's explained, and it's also been discussed for a lot of maybe 60 years already. It's now there might be a little bit of there is a little bit of consensus that it might be due to charge ordering in the outer layers. So within magnetite, why the 100 surface? Well, it's the most important luminous surface, and when one thinks about this application of spin valves and spin injectors, well, if one wants to transfer the spin to another system, it has to, it must go through the surface. So questions like, is the half metallicity conserved at the surface, or what happens to the magnetic properties of the surface are very important. And they're important because this 100 surface is a very polar surface. It has a huge dipole moment, and it undergoes a surface reconstruction, root 2 by root 2 reconstruction. So what are the properties at the surface is an interesting question here. And to the best of our knowledge, there are no magnetic domain studies on this magnetite surface. And our contribution will be to just get a basic understanding, better understanding of this magnetic structure at the surface. So let me start showing you some of our data. What I showed here are beam images, not spin, just beam images. And so we put our bulk crystal with the 100 surface polished into our machine. And we're taking a look after a few cleaning cycles. I was saying before, we don't like ex situ samples so much. They look kind of rough and this texture, they don't look very pretty. These are tuning images of different electron energies. But after many more cleaning cycles and being a little bit patient, you start to see a better surface, a less rough surface. You can start to see the magnetic domains here, but let's not rush into that for a moment. And you see these little rings here, this little circle, actually correspond to atomic terraces. So when one sees atomic terraces, one can start to believe, okay, the crystal might be clean, maybe it's time to start doing some experiments with it. But the second question, okay, it's clean, but is it actually 100 magnetite? It's a sanity check that we all like to do. And we did some big IV curves. So basically study the spotting intensity, lead spotting intensity as a function of electron energy. And what I showed here is a comparison and correlation with the paper from 2008, where they did a very nice study, a lead study on magnetite. And we can see that it more or less nicely agrees with that paper. So we believe that we have 100 magnetite, a clean 100 magnetite. So I'm going to start showing you the magnetic data. This is a lean image, this field of view. And this image, this image corresponding to spin polarization perpendicular to the surface, so we're probing out of plane magnetization. And as you see, there's barely any magnetic contrast. Maybe we see a tiny bit of contrast. We'll get to that a bit later. But when we look in plane, then we see strong magnetic contrast. And then I would like for you to focus on these two images here, which are taken at these two orthogonal spin polarization directions. And And you see the domains that give contrast in the upper picture appear gray on the lower one, like this black one is gray here. One can actually see this domain wall here that corresponds to the domain wall between these two domains. And what this means when you get magnetic contrast at two orthogonal directions is that you actually have two easy axes. This is a biaxial system. And this is due to the fact that in the bulk, magnetic has the 1-1-1 direction as easy axis. This is the 1-0-0 surface right here. But due to the shape anisotropy, the system wants to avoid pattern magnetization at the surface. So it's actually going to bend them into their projections in the 1-0-0 surface that correspond to the 1-1-0 planes. And that's why we get biaxial magnetization at the surface. I show here a collage of a series of spin images, again taking the orthogonal spin direction so that you get a picture of a broader, larger region of the material. And we see, for example, here a white domain and a black domain, and the corresponding orthogonal polarization image. One can very nicely see this wavy domain wall between the two domains. In general, all the magnetic domain structures seem smooth and kind of wavy. And that agrees nicely with the simulations done on magnetite, because when one gets, actually in the bulk, this domain and domain walls are very straight. But when one gets, due to this shape anisotropy bending at the surface, it is expected that the domain patterns are going to change a little bit, be more wavy and more smooth, which indicates that this magnetic free energy is very different at the surface compared to the bulk. Different contributions to the magnetic free energy dramatically change at the surface. It is also worth pointing out that we observed no quasi-domains, which was something that was predicted in some papers at the surface. Quasi-domains which would basically appear as very small domains without plane magnetization that on a larger scale would average out, and we don't see any evidence of that in our work. So combining these sets of 3D images, spin 3D images, one can get the specific magnetization direction at every point in real space, so we can do experimental micromagnetism if you want. And the plan